Good afternoon. In this lecture, I'm going to just do a bunch of examples related to conservation of momentum. So you'll definitely have some conservation of momentum problems. I haven't decided how many. It might be one. Definitely at least one on the final. Tutorial next week will be related to conservation of momentum. So this is kind of the main problem type you'll have for this module of the class. Last lecture, we talked about the integral and I guess simple form of conservation of momentum for a fluid. So what the integral form says is that we can change the momentum of a control volume through momentum flux or applying forces to that control volume. So most of our analysis is based around we have some sort of control volume and um, we want to apply forces to it in order to sort of hold it in place because the fluid's momentum change will require forces to hold things in place. And we're talking about conservation of momentum still, obviously. So yeah, today learning objectives are just to predict forces exerted by fluids using control volume momentum conservation. So we're going to just go through a couple of examples so you can get a feel for what these problems are like. Um, I will be posting homework related to this probably this weekend. So for momentum conservation and hopefully I can get you all of module 5 in there. So that'll be the last kind of practice for the course. Any questions before I get started? Okay. So last lecture, right at the end, we were doing some force balances. I uploaded the notes and I made some corrections here. Okay, so the direction that we assume of forces applied to our control volume is going to be quite important in this module of the class. So I want to highlight, um, first of all, sorry for any confusion about what was going on last class. So this is this is a wind turbine, right? So the fluid is going to exert a force on the wind turbine, spin the wind turbine, and generate energy. So we know that the fluid will basically push this wind turbine to the right. So the direction that the wind turbine is going to be pushed is like that. So that's the direction of the force that's going to be applied to the wind turbine. We're not analyzing the wind turbine. We're actually analyzing the fluid volume around the wind turbine. So the force applied on a fluid volume is equal and opposite. So this is the um, direction of the force applied to our fluid volume. So basically, if we know the wind turbine gets pushed to the right, therefore the force applied to the fluid is equal and opposite. So just like normal dynamics analysis, when you're setting up these problems, you can just you can assume a direction for a force, and if when you do your analysis the number comes out negative, that means the direction you assumed is wrong and it's actually in the opposite direction. So in this problem, these are I didn't write these out in the morning, but it's interesting to look at. So in this problem, we were basically analyzing the change in momentum of our fluid as it enters our CV versus as it exits our CV. So as it enters our CV, fluid has that much, I guess, time rate of change in momentum. So that's a big number as it's coming into our CV. We want our wind turbine to extract some of this energy, which is going to reduce the momentum of our fluid. So that's coming in. This number here is coming out of the fluid. So the difference between those, the change in momentum of the fluid is the force that's being applied. So what you get is a negative number here on the left-hand side. We assumed negative on the right-hand side and we accounted for that. We get a positive number out, which means that the direction we assumed was correct. So just as a reminder, the force applied to the fluid is the opposite direction of the force applied to the wind turbine. So it's an equal and opposite situation. Are there any questions? Yep. It's a really good question. So the question was, could you get the kind of the maximum energy to be extracted by the wind turbine this way? The There is a way to get the maximum energy extracted by a wind turbine. I believe it's more through energy analysis though. So it's not through momentum conservation like this. So it's something called the Betz limit. I think it says that we can only extract, I don't know what the Betz limit is. It's something like say 60% of the energy in a given sort of air tube you can extract using wind turbines. So yeah, if you wanna Google that later on if you're interested. So the Betz limit is really important, and kind of the best designed wind turbines will approach that Betz limit. It's BETZ if you're curious. But really good question. Any other questions about this? Okay, we're gonna see this force direction, assumed force direction, actual today a couple times. So let's get into our examples. So the first example is calculate the force required to hold this elbow in place. So assume our fluid density is 1,000. Let's assume we have kind of pipe flow through an elbow. So the black that I'm drawing is kind of our pipe. Assume we have flow going into the elbow at 1 meter per second, and the area is 0.1 meters squared. Our outlet flow is some unknown V out, and the area is also 0.1 meters squared. Give our coordinate system here. Okay, and I'm also going to note that this is a top-down view. So since it's kind of looking top-down, the elbow doesn't have to support the weight of the fluid inside of it. So that would be in a different axis than the analysis we're going to do here. Okay, so there's our elbow. Our control volume for this we're going to take as something like this. We're going to assume that we have same pressure. Let's say we say P in is 1 kilopascal. Actually, sorry, no, I'm not going to say that. We're going to do pressure later on today, so we're not going to worry about that right now. So our control volume is this green box. Yep. So how you will solve most of these problems is you start with conservation of mass. And then the second step is conservation of momentum. So if we assume a steady state condition, we can use our formula from before. So our mass flow rate out minus our mass flow rate in is equal to 0. So that is rho V out A out minus rho V in A in equals 0. So you might be thinking we have a constant sort of area. Why are you actually doing conservation of mass? Isn't V out just going to be equal to V in? It is, but I'm going to show you the steps through you get to arrive at through which you arrive at that conclusion. So yeah, Aaron. Did I do a pipe before? I think before I just did the stream tube, right? Yeah, so in that case, it doesn't really matter. I guess I made it like sort of just inside the stream tube. In fact, in that, it's probably better to say that I made it the actual stream tube itself. Um, yeah, in this case, the reason like for pipe flows, we're going to make our control volume outside of our pipe is if you make your control volume just inside your pipe, then you have to account for the wall shear imparted by the fluid on the walls of this pipe. So we don't want to have to do that. So we just say our control volume is outside the pipe. So we're only worried about what goes into and out of this pipe and the pressure at the inlet and exit of this pipe. So our rows will cancel, our A's will cancel because A in equals A out, and we get V in equals V out, which is 1 meter per second. So no surprises. We're going to do our momentum conservation now. So I'll draw our free body diagram. So I'm just going to draw these forces on our CV itself. So if you have this elbow in some sort of structure or something in the real world, you'll have like a support. You can think of this elbow was just floating in space. I guess what direction do you guys think the forces are going to turn out to be for this case? What's intuitively, what makes sense? Yep. Up. What makes you say up? Right. Yeah, it's kind of like a rocket or a hose or something. It's going to want to push it up. And what about the another force in the x direction? So that's in the y direction. Up and to the left. So what makes you, I guess if you had like, if we just had a tube in this class and I sort of sprayed water into it, what direction would it go? Probably go the same direction, right? So that's a little unintuitive, but yeah. So if this thing is just going to get pushed this way, and then there's some momentum going out, so it's going up. Yeah, it's correct. So that's kind of where we're going to. Um, if we have an intuitive understanding, we can assume a direction for these forces. Remember that in this analysis, we consider the forces that act on our CV. Okay. So let's say our, let's see, what did I assume here? So the forces that act on our fluid is going to be like Fy and Fx here. Actually, sorry, Fy is going to be downwards. So if you have an intuitive understanding about the direction that this pipe would experience sort of the force, the opposite direction is what happens to the fluid. Okay, but like another trick you can just do is if you just assume always positive, the math will work out that it's going to be negative, and then you know intuitively the direction. So if you assume the wrong direction and get a negative answer, that's totally fine too. You just know that the actual direction is the opposite one that you assumed. Okay, so the conservation of momentum for this case will be this. We're going to use the easy form. And again, this is a vector equation. So this is where we get our x and y force components from, are the different components of this equation. So in the x direction, we have m dot out, but v out, the only component this has is in the y direction. So that's going to be 0 minus m dot in v in. So v in is positive here because it's in the positive x direction. So remember, this is a vector, so you have to be careful about the negative signs. The x forces, we just have fx. Am I going to get the opposite direction here? Oh no, fx I said was a negative, right? So negative fx. Okay. So this means fx is just rho v in a n. That's m dot. So we get 100 newtons. And it worked out to be positive, so that means the direction we assumed was correct. So the fluid is indeed going to be pushed equal and opposite. So that means that the pipe is going to go to the right. The y, well, y is going to be m dot out times negative v out. In that negative, this is probably the most common source of error in these problems you'll make, so that's why I'm emphasizing it so much. The negative is because we're going downwards. That's a vector component, this part. This m dot out is just a scalar. Minus m dot in times 0 is equal to, we assumed downwards for Fy, so that'll be negative. This also gives us Fy equals 100 newtons. So you need a reaction force in both axes. You can think of this as, you know, the fluid comes in and it changes direction. So something has to cause it to change that direction. And then as the fluid leaves the CV, something has to sort of counter the momentum leaving our CV. Any questions about this? If you're confused about anything, the problems just keep getting a little bit harder every time. So feel free to ask if you're confused. Yep. Yep. So this equation here is derived considering the sign of the n. So you don't have to worry about the sign of the n if you're using this equation here. So that's where if you just take m dot and out, that kind of has the sign of the n for outflow baked into it. Same thing for this here. So that has the sign kind of baked in. So we just have to consider about the mass flow rate. We don't have to consider about v dot n when we use this simple equation. Good question. Any other questions? Okay. Let's do a let me see. I'm going to do the kind of longer one now because I think it seems like you guys are understanding this. So this is a kind of a step up in complexity, and that's going to be calculate force required to hold this Y fitting in place. And we're going to assume this would be in the question. This isn't something you would assume. So assume flow rate in branch 2 is v dot over 2. That'll become clear when I show the diagram. The flow pressures have been provided. And we're going to take rho as 1,000. So I think this example will take us a decent amount of time, but I would say it contains basically, it's the most complicated version of one of these conservation of momentum problems you can get. So in this problem we have a Y fitting, and it's called a Y fitting because it looks like a Y. Okay, so here's our fitting. So flow is coming in on the left here. V dot, and it's going to leave like this. So this is 1, 2, 3. Okay, so we're given the following information. So P1 is 172 kilopascals gauge. D1 is 0.152 meters. So this is a pipe, if it's not clear. And that V dot 1, 0.142 cubic meters per second. At the flow in branch 2, we're given also the pressure. Remember in that problem statement, it said V dot 2 is V dot over 2. So that V dot is this flow rate. So this branch, this Y fitting splits the flow rate in half. That's not always the case for a Y fitting. And in the real world, it probably wouldn't be the case for this, seeing as how the branches will have different diameters. But this is kind of an assumption or something you're told about the problem. So there might be cases in the real world where an unequal branch fitting like this would split the flow equally. So at 3, we're given P3 is 165 kilopascals. Sorry. Okay, D2, I forgot to give you 0.0762 meters. Okay. We're given also the angles of these branches. So that angle is 30 degrees. Okay. So that is the problem setup. Our objective here is to calculate the force required to hold this Y fitting. So force is a vector, so we're going to have X and Y vector components at the end of this. So in the last question I said, what are basically the procedure for this? What's the first step going to be? Which conservation law? Mass, right? And then the conservation of momentum. So in this problem, we need to do conservation of mass because we don't know what the outlet velocity is at branch 3. So here's our coordinates. Okay. So like I said, first step is mass. Second step is momentum. And like a reminder, the conservation of momentum is we need all the velocities. So we can't go to conservation of momentum until we know all the velocities, or else we'll have too many unknowns when you set that up. Are there any questions about this problem setup? Okay, it's clear. So our control volume again will be just outside the pipe, so it's going to be the green here. So we can assume, since I provided the pressures in gauge pressure, all we need to worry about are the pressure forces exerted on our control volume boundaries. So if you assume the outside of this is at P atmosphere, which would be provided in the question. Okay, so let's do our conservation of mass. I'm also going to assume steady state. So our outflow in this problem is through branches 2 and 3. And our inflow is through branch 1. So we'll have m dot 2 plus m dot 3 minus m dot 1 equals 0. So m dot 2 is, okay, so m dot 2 is rho v dot 2. M dot 3 is an unknown, so I'm going to leave that. And m dot 1 is rho v dot 1. So I said that this branch, in the question I said that this branch splits the volumetric flow rate equally. Since this is an incompressible fluid, that means it also splits the mass flow rate equally. So we basically expect the mass going into this, half the mass goes to branch 2 and half the mass goes to branch 3. So since I believe I gave m dot 1. Okay, so m dot, so this will, okay, I'll just do this, 1,000. Okay, so m dot 3 will be 71 kilograms per second. We also can calculate the m dot 2s because we're going to need this in the second part of the problem. They're not unknowns, but we just have to calculate them. M dot 2 is the same, right? Because they have the same volumetric flow rate. M dot 1 is double that. So mass is, as a good double check when you're doing this, you can check mass is indeed conserved. So all of our mass going in, we know where that's going. Which, by the way, it sounds really simple, but this is how some leak detection systems work for real-world fluid flows. They know the mass flow rate going into their system and they know the mass flow rate going out. They're able to tell, basically, is there a point in your system that's leaking? Yeah, well, okay. There's more coming out than you think, I guess. That's a good problem. um, but yeah, so that's one of the methods they use to detect leaks in real-world flows. Anyways, so we have our m dots now. We can go to our conservation of momentum for our forces. Are there any questions about the mass conservation here? There's nothing to worry about in the signs for mass conservation, right? They're just scalars. You don't worry about the signs till you get into the vectors. So the signs have been, I guess, baked into this. Before we go there, I'm going to need to calculate a whole bunch of areas and flow rates to make this a little bit more straightforward. So I'm going to use area as pi over 4d squared. So A1 is 0.0181 meters squared. A2 is 0.00456 meters squared. A3 is 0.00811 meters squared. We know the mass flow rates, we know the density, we can get the velocity now. So that will be V is, I guess what will that be? M dot rho. So that will be V is M dot over rho A. So we can get the velocity in each of these branches. Again, it's the average velocity, but in these momentum problems, we're never going to worry about sort of velocity profiles when we have the average velocity. V1 is 7.85. V2 is 15.6. V3 is 8.75. Any questions about how I've calculated this? Okay. So now we'll get to the hardest part of the problem where um, I think is the biggest potential for mistakes. There are lots of sign errors, angle errors, and things like that. So conservation of momentum. So summation over our outlets minus the summation of the inlets is equal to the sum of forces. Okay, so our velocity vectors, they're going to have components now in our x and y directions. Because our outlet flow is coming, our velocity here is actually has a vy and a vx. So one, the first error source is projecting those into the right using the right angle. The second error source is getting the sign wrong when you are getting those velocity components. Okay, so for the x direction, maybe let's, how about this? So for the x direction, just maybe do the left-hand side. Take 30 seconds and do it on your own, and then let's see if we match after. You can always erase it and then write down what I'm going to write down. Just try it on your own because this is really a practice-based part of the course. So just take a stab at it, and then I'll do it. Just the left-hand side. Yeah. I'll show you the solution now. So our outlets, we have flow coming out of 2 and 3. It will be m dot 2. Again, our m dots, we never have to worry about directions, projections, that sort of thing. It's just m dot times v2 sine 30 plus m dot 3 v3 sine 50. These are both positive. The v parts of this are both positive because they're both in the positive x direction, right? And then the sine is here. So that's what we're getting that horizontal component. Oh, sorry. And then minus m dot 1 v1. Our v1 is positive. It's in the positive x direction. Okay. Our force balance will be like this. So this is where the pressure forces come in. So I'm going to assume for the force direction on this fitting, just kind of a fx and a fy like this. Let's say I don't have any intuition about how the forces are going to come out. I think it's hard to have an intuition about what direction the net y force is going to be on this because you have two outlets. So the pressures are different, velocities are different. So I'm just going to assume that and show you what it looks like when it comes out negative. So our forces are Fx plus the pressure force at the inlet, so Fp1 minus the x component to the pressure force. I'll write this down and then I'll explain what these minuses come from. So the pressure force at 2 times sine 30 minus the pressure force at 3 sine 50. So I'll talk about the reason that these are minuses now. So remember that pressure always acts normal to the surface. So our pressure force at 1, this is kind of a plane with a given pressure. It's acting on our CV and it will act normal to that surface. So that's in the positive x direction. The pressure force at 2 and 3 This is confusing, so I know this is confusing. It acts inwards. So that pressure force acts to press on our CV like that. So those have negative, that's where the negatives come from. And we're also going to use FP is pressure times area. So that's how we get the force due to pressure. Okay. Yep. Yeah, and that one, this problem, I can't exactly remember the setup. I think maybe we were saying like that this was at atmospheric pressure or something like that. So there's no net pressure force on the CV. We're just calculating the momentum change of the fluid. So a good question because it's also an internal flow. So um, yeah, it will be I guess clear if you have to account for pressure forces if it's not atmospheric. I would say in general, like it's the pipe flow problems like this that you have to start accounting for those pressure forces. Any other questions? Okay. So there's going to be a whole bunch of numbers now that I'm going to write down. So that's m dot 2, 71. V2 is 15.6 sine 30 plus m dot 3, also 71 times 8.75. So that's V3. This is why I calculate all these pressures and velocities and areas before going into this. Times sine 50 minus m dot 1, which is 142 times 7.85. That's going to be equal to fx plus r. So this is P1A1 here. So this is P1A1. Okay, this is going to be P2A2. This is P3A. So this is P2A2, and then that's the projection into X. And this is P3A3. Projection. I'm gonna just quickly check those. Sorry. Yeah, okay, that's okay. So yeah, this is, you can see this is starting to look like basically a long answer problem on an exam, and yeah, it will look something like this. Like there's just a ton of numbers and things to keep track of. So this is what it looks like. So fx is equal to, I'm going to group some of these numbers just for our understanding. So this first number is our summation over our outlets of m, basically Vx, the x component. So there's just that one inlet. Oh, sorry, that's 1114. And this one is the pressure. So we have, yeah, we are losing some like x momentum components plus the pressure. This gives you a rough idea of the magnitudes of each of these components. So they're all pretty similar in magnitudes. That's why we need to account for pressure. Yep. Oh, the area projection. So we're not really projecting the area. We're projecting the pressure component. So this is a circle kind of like this. So the pressure would create a force like that. We're just taking that and getting basically the x component of it. We don't need to project the area. You just calculate the force due to pressure in that direction and then project that down. Any other questions? Okay. So we get negative 1975 newtons. So that means that the actual force is in the opposite direction. Okay, so that is one of our forces. And we also have to do this entire analysis in the y direction to get the y component. So are there any questions about maybe where these numbers come from now that you've had time to stare at them a little bit longer? No? Okay. So the y, how about give you guys 2 minutes to do the y. You don't have to do the numbers, but do both sides of this equation. So do the mass, the momentum balance on the left, then the force balance on the right-hand side. And then I'll write it out and give you the answer. Again, I'm sure as you're doing this, you're seeing like, oh, what is the sign again? What is the sign again? So this is just definitely a practice heavy part of the class. Anyways, I'll stop talking. I'll give you the answer now. So this is going to be m dot 2 v2 cos 30. So the cos comes from the y component to this, plus m dot 3. Again, this whole thing is the first summation. In this case, this will be minus v3 cos 50. So this minus, I want to emphasize this quite a bit. This minus is because the y component of here is downward. So the y component of our outlet, 3, is minus y. Again, our inlet doesn't have any y component. Then the force balance will be Fy minus Fp2 cos 30 plus Fp3 cos 50. So minus Fp2 cos 30 is because the pressure force acts inwards to our CV. So that's going to have a negative y component. At 3, the pressure acts upwards. So it's going to have a positive y component. We don't have any y component from 1 in our y pressure force. Any questions on that? I'm not going to write out the several lines of numbers again. I'll just look at the answer here. So we get Fy equals 560 minus 516. So this is the momentum flux, and then this is the forces being applied. So 44 newtons, and again, we got it positive, which means we assume the right direction. Yeah. So any questions on this? Where these signs come from? Yep. Okay, yeah, I'm just trying to show you the balance of the terms. So this first term is this. So that's the sum of our momentum leaving our system in the x direction. The second term is this. So that's the sum of our momentum entering the system. Oh, sorry. Yeah, no, this should be Vx. Is that why you were confused? Yeah, my bad. So we're just in the x direction here. Yeah, my apologies for that. Yeah, so that makes sense. Any other questions? So again, these problems are, once you do some practice, it'll be good. So that's why I'm going to try and have your homework posted by this weekend. Next week, the tutorial will definitely be on practicing these conservation of momentum problems. There's an interesting equation that I can do. So is there any more questions about this example where these positives, negatives, projections have come from? Okay. There's a famous equation that's used to calculate the thrust of a rocket engine. And it comes from this sort of analysis we're doing here. So if you have some sort of rocket engine, I don't know if you've seen a lot of these, but they look something like this. In fluids too, you'll learn all about what's actually happening in this. But you basically take a control volume like this around, say, your whole rocket. So we can't really put things into our rocket. When the rocket leaves, we're only stuck with what we have in there. So the only way we can create thrust for the rocket is to throw things out of the rocket. You can think of it that way. You can't you can't really get things into a rocket that's flying through the air. So the only way it can power itself is by throwing things out of it. So this has some sort of exit velocity and also some exit pressure. The atmosphere around this rocket has some pressure P0. So the force of thrust is equal to this m dot VE. That's called the velocity thrust. And now, since our outlet, you can't really assume this is at atmospheric pressure anymore. So sometimes we assume when we outlet things to atmosphere that it's at atmospheric. We make that assumption most of the time in this class. But for a rocket, the outlet is at such high pressure, high temperature, you can't really assume that. So you actually get a little bit of a pushback from the pressure at your outlet. It pushes on your rocket a little bit. So you get a little bit of extra thrust from that pressure. So that's P minus P0 times the area of your exit. And that's called pressure thrust. Okay. It's an interesting equation. So any other questions about this? No? Okay. Well, have a good weekend, everyone. I'll see you on Monday.